Hey everybody, this is Unit 5, Video 3, and I'm gonna be showing you some strategies that you can use as you verify trig identities. Alright, so when we verify a trig identity, we're trying to show that the two sides of our equation are equivalent. In other words, that they actually have the same value. Something similar to this would be like, well, I want you to show me that the square root of 4 plus 1 is actually equal to 2 plus 1. So this is a very basic example, but we know that it's true because we know the square root of 4 is actually a 2. So we could use some replacement. And this could be done obviously in a much more complicated way. And the way we're going to be, what we're going to be looking at is actually trig. So we're going to be using all the identities that we know from the first two objectives. So I'm going to propose a few different strategies to you. These strategies are also listed on page 194 in your textbook, so you might want to write that page number down because it'll give you something to reference if you get stuck on going through some of these. But remember, our goal here is to transform one side of our equation to look like the other side. We're going to leave one side alone and we're going to change the other side. So let's go ahead and talk about some strategies to do this. The first thing you need to know is you have to know your identities. You must be familiar and comfortable with replacing all of the identities and recognize them when you see them. Just like if every time you were to recognize a number, if I were to throw the number 49 out at you, you should be able to go, that number sounds familiar. It's a perfect square. Or the number 25. To know that 25 is a quarter of 100. Or know that 25 is also a perfect square. So knowing what these numbers are and these trig identities are and familiarity with how you can use them is the key. The next thing is we're going to be working on the more complicated side of our equation, and we're going to make it look less complicated. So it's going to seem strange to want to attack the ugly side of the equation, but since it's going to be easier to attack the ugly side of the situation or the equation, that's what we're going to be doing. So I'll explain as we continue. Use the sine and cosine replacement. That's the first strategy I'm going to demonstrate for you. So what we talked about in replacing everything else to make it look just like sine and cosine, and then we get to simplify. So let's start on that one. So here I've got cotangent of x plus 1 equals the cosecant of x times the quantity cosine of x plus sine of x. So I look at these two sides, and the first thing I want to do is figure out which one is more complicated. I think the left-hand side or the right-hand side is more complicated. So we're going to leave the left side alone. I'm not going to touch it at all. I'm not going to subtract things back and forth. I'm not going to multiply both sides. I'm going to leave that side alone, and I'm going to transform the right-hand side to look like the cotangent of x plus 1. To do this, I'm choosing the replacement method. I'm going to replace secant of x with 1 over sine of x. Cosine of x plus sine of x get to stay because they're already in terms of sine and cosine. And now I'm going to distribute. So I get the cosine of x over the sine of x plus the sine of x over the sine of x. That's my distributive property. And I know that my cosine of x over sine of x actually is cotangent of x, and sine of x over itself is 1. So I was able to take this more complicated side, and turn it into the simpler side, cotangent of x plus 1. This is a very simple example of verifying a trig identity. The next thing we're going to look at is how to add fractions. We know that if two fractions have the same denominator, that we're able to add them together by just changing the numerator. However, if they have different denominators, then I have to find a common denominator before I'm able to add or subtract the fractions. So I would multiply this one by 4 over 4, this one by 3 over 3, leaving me with 4/12 plus 3/12, so that I could finally just add my numerators and leave my denominator alone to come to 7/12. So this idea of the 4 over the 4 and the 3 over the 3, which really represent 1, but a very particular value of 1 so that we can manipulate these fractions, is what we're going to be doing in the next example. Let's take a look. So on the top here, I've got 1 over the sine of alpha minus 1. Minus 1 over the sine of alpha plus 1. I don't have a common denominator. My common denominator is going to be to multiply these together. So my common denominator is the sine of alpha minus 1 times the sine of alpha plus 1. In my example with the 1/3 and the 1/4, what we chose was to multiply the 3 times the 4, which came out to a nice numeric answer of 12. Since sine of alpha minus 1 and sine of alpha plus 1 don't have a numeric niceness to them, we have to leave them in this more complicated looking manner. So if I multiply this one by the sine of alpha minus 1 over the sine of alpha minus 1, that gets me the denominator I'm looking for and changes my numerator. I'll do the same thing over here, the sine of alpha plus 1 over the sine of alpha plus 1. That's like multiplying by my 4 over 4 and my 3 over 3. My numerator on the first part of the fraction becomes just the sine of alpha plus 1 because I'm multiplying it by 1. However, on the second side of my fraction here, I'm going to have to distribute the negative 1. So be careful when you're doing that because you're actually multiplying by a negative 1, leaving me with negative sine of alpha plus 1. And that's a negative times a negative will give me this. My common denominator is actually sine of alpha minus 1 times the sine of alpha plus 1. To simplify my numerator, my sine of alphas cancel, and I just get a 2. To simplify my denominator, I'm going to change colors. I'm going to distribute here and get sine squared of alpha plus sine of alpha minus sine of alpha minus 1. The middle terms cancel, and I get sine squared of alpha minus 1. And this is my final simplified answer of adding those two fractions together. So let's go ahead and see how we can apply that to verifying a trig identity. Please notice in the first example here with the sine of alpha on the top, there was no equal sign. I was not verifying. I was simply simplifying. But this one, because I want these two sides of this equation to look the same, this is a verifying example. So I'm going to leave my very simple side alone, and I'm going to turn this ugly side into negative 2 tangent of x. So using the same method of multiplying by the tangent of x plus secant of x on this numerator, and the tangent of x minus the secant of x onto this numerator, I want to avoid the words cross multiply because I am not cross multiplying. I'm finding a common denominator. To cross multiply, I would have to have an equal sign between the two fractions that I'm working with. And in this case, I have an addition sign. So I'm not going to use the words cross multiply. But I am going to multiply this onto this side, leaving me with tangent of x plus the secant of x on the first fraction, and on the second fraction is tangent of x minus the secant of x. So my common denominator will have both of these pieces in it, and I can go ahead and distribute just like we did up here in my denominator using your arrows or FOIL if you want to call it that, leaving me with tangent squared of x. My middle terms will cancel because I have opposites, and I'll have minus secant squared of x. All right, so my numerator gets cleaned up where my two secants cancel, and I get 2 tangent of x. So it looks like I'm on my way towards this negative 2 tangent of x. So perfect. My numerator is looking good. My denominator, however, is tangent squared of x minus secant squared of x. So I'm going to reference one of our Pythagorean identities that I have tangent squared of x plus 1 equals secant squared of x. And it looks like I would rather find a way to get rid of my secant since I don't have secant in my final desired answer. No secants there, so I want to kind of get rid of the secants. So I'm going to replace this secant squared of x with tangent squared of x plus 1. I do have to be careful here because as I replace tangent squared of x minus, and I put in this tangent squared of x plus 1 in place of my secant squared, I am subtracting the entire quantity. If I don't put a parentheses around this, then I'll end up with a positive one here, and I don't want a positive one. So I get tangent squared of x minus tangent squared of x minus 1 when I distribute, which leaves me with exactly what I want, a divide by negative 1. And I get negative 2 tangent of x, put the box around it, put my check mark, because I was able to verify this trig identity. The next one we're going to be looking at is ways that we can either factor or expand binomials. So I'm going to focus on the factoring one, and we can talk about the expanding one as well. But the factoring one. So here I have an expression that I just want to use as an example of how we can factor. Here I see that I have a GCF. It isn't the only type of factoring we can use, but it is a very common one for verifying trig identities. So I'm going to factor out my GCF of sine. So if I take out a sine of x, I'm left with 2 times the sine of x plus a 3. Think about this in reverse. If you were to distribute, would you get back to the original expression? If I were to distribute this sine of x, I'd get negative 2 sine squared of x. And if I were to distribute it over here, I'd get 3 times sine of x. So in fact, just using a GCF was really helpful here in order to simplify this. So let's see how we can work that on this verifying trig identity problem. First of all, what side is more complicated than the other? In this case, I don't know if one is more complicated than the other, so you're more than welcome to work either side. I'm going to go ahead and work the cosecant side and leave the cotangent side alone. So if I go ahead and just put a box around this side, I'm not going to touch it at all. I am going to be manipulating my cosecant side by pulling out a common factor of cosecant squared. So cosecant squared of x, if I factor that out, I'm still left with cosecant squared of x minus 1. Think about distributing that and see if that makes sense. All right. So my cosecant squared of x, using one of my trig identities, that cosecant squared of x is equal to cotangent squared of x plus 1, then I can replace this cosecant with cotangent squared of x plus 1. Now, I can then replace my cosecant squared of x over here with the same thing. So I get this. I get cotangent squared of x plus 1 is the first replacement. And then my second one is going to be cotangent squared of x plus 1 minus 1, which will simplify down to cotangent squared of x plus 1 times cotangent squared of x. If I distribute this backwards, I get cotangent to the 4th power of x plus cotangent squared of x. And that is exactly what I was looking for to verify this. So let's recap that problem. The first thing I did was I factored out a common factor between these two terms on my left-hand side. That was a cosecant squared of x. The next thing I did was I looked at my relationship between what I had, which was cosecant squareds, and what I was going towards, which were cotangents. So I knew I had this Pythagorean identity. So I was able to then replace in both situations cosecant squared of x with cotangent squared of x plus 1. It simplified down to something that I was then able to use the distributive property and finally come to exactly what I was looking for. So as you go through these problems in this objective here, you're going to have to be referencing a few different strategies. You should always start with, can I just use replacements? Replacements will work for most of them. However, you're going to come to some where they require some algebra, such as GCF, such as a common denominator, and perhaps even some distributive property methods. So take your time as you go through them and make sure you ask questions along the way.